going to do this again tomorrow probably. I'm sure that other students will ask, but it's good to see it. I don't think we haven't done them all together, so is that okay if we do the free response first? And then if y'all have specific questions, we can go through and look at the multiple choice. But it's going to look like this. This is last year's exam for chapter 1. In fact, your exam will look a lot like this exam. And for the free response, I basically just copied and pasted these 3 questions, and I just changed the figures and changed the numbers. So it's almost identical to this. It just the numbers will be different. So the first one, I just want you to the result of these 3 parts, 4 parts, is to give me the resultant of the electric field. So it's a 2D vector sum is effectively what you're doing. First part is sketch the electric field vectors and calculate any angles. So I'm looking for the electric field at that point. And so I sketch it in first. I imagine a positive test particle there, a positive test particle. See, I'll call this Q1 and Q2. The electric field due to Q1 is going to be in that direction. The electric field to Q2 is going to be in that direction. That's E2. And then I also need to find the angle. Oh, shoot. I don't have a distance there. It must have been 8 meters. No, it was 12 meters. Okay, yeah, because it's a 3, 4, 5 triangle. So it's a 12 meter right there. And if I wanted to know the angle, that would be this angle right here. So I want to find theta. So theta is the, let's see, this is my triangle right here. The inverse tan of 12 over 9. So that is 53 degrees. I don't know that tangent, but it's a 3, 4, 5 triangle, and the big angle is 53 degrees. So anyway, you can calculate that angle. That's part A, sketch the electric field vectors and calculate any angles. Part B is to find the X and Y components. So I like to redraw this as a picture. I have E1 right here, E2 right here at 53 degrees. I want to now calculate what E1 and E2 are. So E1 is going to be KQ over R squared. That's 9 times 10 to the 9th. Q is Q1. That's 9 times 10 to the minus 9. Divided by the distance. That's going to be this distance right here. So 9 squared. I try to make it so that a lot of the numbers just cancel out. So do that, please. It makes your life a lot easier. So notice these cancel out. This is 9 times 9. That cancels out with that. So if they all cancel out, that doesn't leave 0, of course. That leaves what? 1. That gives me 1. And then E2, I do similarly. 9 times 10 to the 9th. 75 times 10 to the minus 9. Divided by the distance, which is 15. Yeah, so 15 squared. Oh gosh, what is that? So these cancel. I get 3. So that's equal to 3 newtons per coulomb. Newtons per coulomb for both of those. That should be a newtons per coulomb over there. So now I have that. This is equal to 3. This is equal to 1. Now I can resolve that vector into its x and y components. So I have a component right here. That's going to be 3 cosine of 53. This is 3 sine of 53. And then E1 is right here. It's just 1. This has a value of 3 cosine 50. Is 1.8. I'm going to keep 2 sig figs, and this is 3 sine of 53. That's 2.4. Okay? Everybody with me so far? I know this is fast, but adding 2D vectors, right? We've done this before in class a number of times, and we did it last semester too. So the next step is to add up those vectors that are along the same axis. I like to redraw the picture. You have plenty of space on the page, so you know, why not? And I'm going to have a vector here that's in the negative direction. That is 0.8 newtons per coulomb and 2.4 newtons per coulomb. And now finally, I want to find the resultant vector. That's going to be this vector right here. I want to know the magnitude of it and the direction. So to find the magnitude of that vector, I say that the electric field, the magnitude of it is the square root of 0.8 squared plus 2.4 squared. I didn't. So what I did there is I said 1 minus 1.8, and that gives me negative 0.8. That's why I draw this just as 0.8. I added those two vectors that are along the x-axis, but since one of them was negative, it came out to be negative 0.8. Okay? Y'all follow me on that? Everybody with me? All right. So I have the square root of 0.8 squared plus 2.4 squared, and that's 2.5. So I get 2.5 newtons per coulomb. That's the magnitude, and then I also want to know the direction of the electric field, and the direction of the electric field is going to be this angle right here. I'll call it phi. Phi is the inverse tan of 2.4 over 0.8. Right with me on that? Where that came from? Well, I have a triangle right here, here, here. This side is 2.4. This side is 0.8. That's opposite over adjacent. So that gives me now the inverse tan of 2.4 over 0.8. That's the inverse tan of 3, which is 72 degrees. All right, that means that this angle right here is 72. I want it measured counterclockwise from the plus x-axis. That will be true on your exam on Monday too. So I don't want that 72 degrees. Instead, I want this angle right here. And so I would say 180 plus 72 is what? 252 degrees from the plus x-axis. So make sure that you're adding in the appropriate amount in order to measure it from the plus x-axis. Be careful on that. So if you get the 72, you'll get most of the credit, but I will take off some. And then finally, so those are the, I'm already looking for these values. And if you have that, I'll sort of glance over your work, and hopefully everything is right, and it'll be an easy thing to grade, and you'll get 100. And I'll have to go start picking and see what you have. Probably not. Probably definitely not going to full credit. I'll get the right answer, but honestly, like I can, if somebody gets every question right, I can grade it in like 5 seconds. Just get it right. Everybody's happier. You're happier. Right? Yeah. Okay. Then the final part is just to calculate the potential at point A. So that's a little bit different. I want to know the potential here. Remember, potential is the sum of the individual potentials. These are scalar, so there's none of that business. It's just a straight up sum. So I have KQ over R for Q1. That's 9 times 10 to the 9th. Times Q1, which is 9 times 10 to the minus 9, divided by R, which is 9, plus 9 times 10 to the 9th, negative 75 times 10 to the minus 9. Remember, when we're calculating potential, which is a scalar quantity, we keep the signs. Okay, the signs are relevant there. Divided by the distance, which was 15, right? 15? Yeah. Then I can go and cancel some things out. I make the numbers so they work more easily. Those all cancel out. One of these cancels with that. I can get 9. 15 goes instead of 5, what? 5 times. So this cancels with that and leaves 5. 9 minus 45 equals negative 36 volts. All right, so that's the answer for part E. It's a little bit different, but it's easier than all the 2D vector stuff. You with me on this? Come back and look at it if we need. The electric field lines are pretty straightforward. in this case, recognize that I have a 2-to-1 ratio. I should have twice as many lines for the -2 as I do for the -1, and then also field lines go into the negative charge and out of the positive charge. In this case, because they're the same charge, I mean they're the same sign, the field lines will come out like this. Oop, I got that wrong. They'll go in like this. And if I have 4 on that side, that means I'm going to have 2 on that side. And then to draw the field lines, or excuse me, the equal potential lines, I'm just looking that the equal potential line is perpendicular to the field line. And that means that the equal potential line will curve around like this. Notice that each line is perpendicular. I'll allow some, tolerance on that, but I want to see, yeah, that would be an A plus, 100% of that. Okay. And then finally, for this last part, we've done this once or twice in class, but not very much. The big overarching idea is that a change in potential is a change in energy over Q. Right? I say potential energy, but it's also true for the kinetic energy, because any change in potential energy will be mirrored by the kinetic energy. But that's the equation that you have on your equation sheet. So I have an electron that goes from here over to there, and I want to know what is the speed of the electron. And so for part A, I say that delta V is equal to the change in energy. I'm going to do kinetic energy here divided by Q. The reason I switch those out, the reason why I can do that, because anytime I have a change in potential energy, I have the same change in kinetic energy. It just, if one goes down, the other goes up. So my change in kinetic energy is equal to Q delta V. There's actually a negative in there, but don't worry about the negative. We're just looking for the magnitude of its speed anyway. That's going to be 1/2 mv squared equals Q times delta V. And now we can notice those V's are different quantities. One's the speed, one's the potential. I'm looking for V. So that's going to be the square root of 2Q delta V divided by M. I'm not going to put all the numbers in. Q is the charge of the electron. I'll write that over here. It's 1.6 times 10 to the minus 19 coulombs. That's on your equation sheet because it's an electron. The mass of an electron is 9.11 times 10 to the minus 31 kilograms. That's also on your equation sheet. So when you get this problem, it's either going to be a proton or electron. Make note of that and recognize that you know the mass and charge of that particle. Then delta V, I'm going from 6 to -3. It will go from a positive to a negative or a negative to a positive. So you're not just adding those two quantities together. The change in potential is how many volts here? Is it 3 volts? No, it's what? It's 9 volts, right? Because I'm going from 6 to -3. So that difference in potential is equal to 9 volts. Going from what? Okay. So there is a sign, like depending on which direction you go, you'll have a negative potential or a positive potential. Don't worry about all that. That gets all washed out in a kinetic or potential energy. I just want to know the speed. I just want to know what is the absolute value of that change. 9 or -9, but that doesn't really matter. Don't get all wrapped up in that. But what I do know is that the charge times the change in potential is equal to the change in kinetic energy. Okay, don't worry about the signs. It's important, but not important for us. So once I get that, then I can figure out what is the speed of that particle. Okay, and then for the electric field, oh goodness, I ran out of space here. For the electric field, just don't forget, I'm going to go back and show you the equation sheet. So the electric field is related to the change in potential in that way, that delta V is equal to -EX delta X. Again, the signs are not important, so we're just looking for the magnitude of the electric field, but that V is equal to E times delta X. So V is equal to E times delta X. So if I'm looking for the electric field, that's going to be V divided by delta X. I know what V is. That's 9 volts, my delta V. My delta X is 0.3 meters. And so that's, what is that, 30 volts per meter. I did that right? Yeah, 30. Yeah. Okay. So that's my electric field, the magnitude of my electric field. Alrighty? That's all your free response. So that's 8 of the 28 questions on your exam. It's a good chunk of your exam. Practice those. Like, you should be able to do them without thinking. You only have to think about it. And now today is a good day to master that, because as you move into the weekend and studying for the other stuff, it'll really help you, because you'll have similar questions throughout the multiple choice part of the exam. Questions about that, y'all? Okay. Threw a lot at you, and we're going to see that again tomorrow, so you'll be thinking about it over the next day. We're going to see it again. But the last 3 years or 4 years of exams had very similar problems to these. Practice each of those with different numbers and stuff. What changes when you change the numbers? They don't really change that much. I mean, you might, no, they're basically copy and paste. That's what I did. Copy and paste. Change the figures and the numbers, but they're the same question. All right. How is that for free response? Is that similar difficulty to what we've had before from last semester? Is that more difficult? It's more work. Yeah, it's the 2D vector stuff. Like that, there's a lot of steps there, but it's important to me that y'all know how to add vectors in 2 dimensions. So that's why we're doing it. There's not really a whole lot of physics. I mean, there's the finding the electric field and knowing how to, find the direction of it and all that, but most of it's just vector addition. I will get partial credit, and I'll try to be gentle with it, so a little gentler than I usually am. All right, let's look at some of the free response, the multiple choice. So it's going to look a lot like this exam as far as the distribution of questions, that there will be 3 or 4 that are just about, static electricity. This is about the fundamental unit of charge, the basic properties of charge, about charging by conduction, that requires contact between 2 surfaces, charging by induction, that no contact. So you'll see some things like that are just 3 or 4. I think there were 4 questions that are just asking you about the properties of charge. Look back at some of those. You'll see similar questions to those. And then there will be some about Coulomb's law. You'll probably have one, something like number 5. It's a lot like what we did, but simpler in the free response. The direction of the force acting on Q1. Well, I know that in this case, that force is in that direction, and then it's a matter of doing the trig to figure out what is the direction. I will caution you. I know that this angle, if I do the trig, I can find this angle is 37 degrees, so this angle is 53 degrees. So that's the angle. A is the 53 degrees above the x-axis, but I might not express it in that way. If it's in another quadrant, I might express it measuring from the x-axis. So just be careful that you're not just looking at the numbers, but you're also looking at the reference point. Because that's very important. Because it could be one of the other answers, and you just pick 53. Well, it looks like 53 is there twice. Below the x-axis. What is the x-axis? I don't know. What? Hugs and kisses. Just hugs. Yes. Is the O's are kisses? And the X's are hugs? Oh. You need a grandmother or something. I'm sorry. Maybe your grandmother passed or whatever. You're going to have one? Move on. Number 6, you'll have one like that, either about electric forces or potential or electric field. Anytime you see one of these, like where something's changing, then you just write down the equation. So I know that the Coulomb's law is F equals K, Q, Q, or R squared, and then I go back in and I say, well, what's changing? If I double one of the charges, if this doubles, and I move the charges to 3 times their original distance, so that triples, how does that affect the left-hand side? Well, I get a 2 in the numerator and a 9 in the denominator. I say 2/9 times 12, 8, I think is the answer. All right, so is that not right? That's what I said. 2.7 is the right answer, okay? But just follow it, even if it's about electric fields or electric potential, write the equation. Don't try to do it in your head. I can't do it in my head, so I don't think you can either. Write the equation, and then just, you know, in a different color or in a different whatever, however, I know you probably don't have a different color pen, but write down how each of those variables changes, and then whatever you do to the right-hand side, you also have to do to the left-hand side. Pretty sure you're going to see one like number 7, where I'm asking where is the electric force or field or potential equal to 0. Remember, as a general rule, you're trying to get away from what? The big charge. Because if I move away from the big charge, it minimizes its contribution to whatever it is, the force or the field or the potential. And I get closer to the smaller charge, it maximizes its potential. So that's a good general rule. Doesn't always work, but it's a good general rule. I would start here. So we'll just go with each option. I want to know where the net force is 0 newtons. If I'm in the middle, I have a net force due to this charge that's in that direction, and due to this charge that's in that direction. Notice I drew that second vector bigger. And then also notice that if I have, because of how these two vectors are drawn, that I cannot have a 0 force anywhere in between those charges. So I can't have it at x. I can't have in between either of those charges and the little x in the middle. So I could guess that it's going to be what right now? What would you guess? B. And you would be right, but let's just confirm that. So if my general rule is true and I just want to get away from the big charge, let's draw our force vectors for over here. I'm placing a charge here, either positive or negative, so I'll imagine a positive charge there. I have a force due to the plus q that's in that direction, and to the negative 4q that's in that direction. There is a place over there where those two are equal but opposite, because I get a smaller force, I get a bigger force due to the smaller charge because I'm closer to it, and I get a smaller force due to the bigger charge because I'm farther away from it. So somewhere to the left of the plus q is where I'm going to have that. Now, I could imagine that there's a negative particle, and the same thing would happen. It's just the two vectors would flip-flop, but it would still be the same answer. All right. Again, this is quick. Y'all pause me if you just want me to pause or explain. You're going to have one like number 8 and like number 9 for certain, where I just ask you what is the magnitude of the net force on Q2, and you just have to, well, in this case, I would draw the force vectors. Both of those are positive. Let's see, one force vector is going to be that way and the other is going to be that way. You calculate the magnitude of each force and then subtract the negative from the positive. You're going to have one like this. We did something like this in class. I always start with a smaller charge when I do these, and I say, well, this force is going to be in that direction. And then I have one that's twice as far away and twice as big. So remember Coulomb's law. If you write down the equation at this point, if I'm twice as far away and I have twice the charge, that's 2 over 4, I'm going to have half the force. So my force due to that one is going to be in that direction. That means that B is the right answer. If they were the same, it would be C. If this one's bigger, the result is going to be closer to that one. Okay? Yes, going to have one like that, very similar to that. It would just be a different configuration, but work in the same way. Know what fields and forces and potential. Field is a force per charge, potential is an energy per charge. Here's another one of those where you just write down the equation and ask, what happens when I change the variables? Here's another one where I'm asking, where is the E field 0? So it's similar to that previous one that we did. Where is the electric field 0 here? You're going through and you're sketching out the vectors for each of those. You're going to have one like this. Man, you're going to have one like all these. It's very similar to this exam and every other exam. They're all really similar. So what is the sign and magnitude of Q3? Well, Q3 I know is positive or negative. Negative, because those lines are going in. So that means I can get rid of C. And then I'm telling you that Q1 is 12 coulombs. I like to look at that and say, well, how much is each line worth, so to speak? That's the way I approach these. So if that's 12 coulombs, that means that each of these lines is 3 coulombs. They're not really. That's just the way I think about it. Does that help you to think about it that way? So if they're 3 coulombs each and Q3 has 6 lines, that means that Q3 is 18 coulombs. And I know it's negative 2, so D is the right answer. You see what I did there? There are 6 lines. 6 times 3 is 18. Really, I'm doing the ratio by doing that, but I find that to be an easier way when it comes to charges to think about it. All right, there's going to be some similar to this. I have a charge that's moving around in an electric field. Positive charges move from high to low potential. Negative charges move from low to high potential. I always remember my mountain. Positive charges will roll down. Negative charges do the opposite. They roll up. Or I can remember that high potential is positive, low potential is negative. So, of course, this one would be attracted to the negative side. It would move in that direction. Or I can think about my electric field. My electric field is in that direction from high to low, from positive to negative. And so that particle is going to move to the right. Several different ways you can think about it in terms of forces, fields, or potential. Either one of those ways would be correct to think about it that way. Remember, those are the big ideas. Forces, Coulomb's law, fields, a force per charge, and potential. That's an energy. All right, you're going to have one like number 17. I don't think I had one where there were 3 lined up like that. I don't remember, but there's definitely one like here where I'm asking, where is the potential, the equipotential line, always 0? In this case, along the x-axis. And in this case, you're looking for one where the distances to oppositely charged charges is always the same. Do y'all know what the answer is here? None of them, right. Because, for example, right here, the distance to the negative charge there is bigger than the distance to the positive charge. So those potentials do not cancel out. They don't add up to 0. There is a point on there, a single point right in the middle where the potential is 0, but not all along the line. So D is the answer there. Y'all probably work this exam, huh? You're going to have one like 18. Practically identical to 18, in fact, where I'm just giving you like every question. I seriously am. The exam looks almost identical to this. I'm serious, okay? So you have to do that where the best way to do that is to calculate the potential due to these two, and then whatever that is, the potential due to this one has to be the negative of that, and then solve for what that charge is, all right? And then for this one right here, if I have a 2 coulomb charge at point A, so I have a plus 2 coulomb charge, it's going to move from high to low potential. So it's going to roll downhill, so to speak, into that low potential state, into -6. It's going to have a delta V of 18 volts because it went from 12 to -6. That's a difference of 18 volts. I know my sign is wrong there, but again, I'm not really worried about the sign. And if I want to know the energy, remember that potential is energy over charge. So I'd say 18 is equal to PE over Q. And Q in this case is 2 coulombs. So the energy then is now 36 joules. It is going to gain that much energy as it rolls down that hill in that potential, that's a potential well. It rolls down into that potential well. Not actually rolling, but we can think of it in that way, like a ball rolling down the mountainside. And then number 19, you're going to have one like this. So the easiest way to think about this is the potential energy is KQQ over R. Actually, it looks almost the same as this. K and R are the same for all of these. That's why it's on an equilateral triangle. So to find the potential energy total, I consider each of the three pairs. There are three distinct and unique pairs, and each of them has an energy wrapped up in that pair. This one would be 8. It's not actually 8 joules because I'm not including K and R, but I'm just looking for the sign of the energy. This one would be -8, and then this one would be -4. So I add those two up, and I get an overall negative potential energy. Okay? That's the exam. I mean, not all those questions, but all those ones that I said, these are on the exam. It's very simple. And the one before that is similar, and the one before that, and the one before the last 4, 5, 6 years are all very similar. Y'all have particular questions? I know it's not ideal to have help session 2 days. Friday's out from the exam, right? But Fridays don't work for me very well. So, is that helpful to you? Yeah. We're going to do something similar tomorrow. We won't work all those. We'll look at maybe the previous year. That in class tomorrow too, and others might have particular questions. All right, don't leave. Let me just make sure I get everybody's name, and then y'all can go.